A radar system connected to a radio telescope has long been one of the most powerful tools available for studying small bodies within our solar system, allowing astronomers to obtain direct information about the size, rotation, and surface features of asteroids and comets that pass near Earth. This technique first demonstrated in 1968 with a successful radar observation of asteroid 1566 Icarus, transformed our ability to image these distant objects by bouncing radio waves off their surfaces and analyzing the returning signal. If conditions are favorable, meaning the object is sufficiently large, reasonably reflective, and comes within an accessible distance, radar can produce detailed echoes capable of revealing a three-dimensional shape, rotation period, and sometimes even surface roughness or structural irregularities. Extending this technique to interstellar visitors is naturally an enticing possibility, because unlike typical solar system comets and asteroids, interstellar objects arrive from outside our planetary system, and therefore provide rare glimpses into the composition and behavior of bodies formed around distant stars. With that in mind, I carried out calculations to examine whether the recently discovered interstellar object 3I/Atlas could have been imaged using existing radar systems, such as the Goldstone Solar System Radar, or, formerly, the Arecibo Observatory. Although its actual trajectory brought it no closer than 269 million kilometers from Earth on December 19, 2025, a distance far beyond the practical limit for radar detection, the analysis showed that if Earth had happened to occupy the opposite point of its orbit, essentially the position it held 6 months earlier or would again occupy 6 months later, the encounter geometry would have been dramatically different. At that alternate location, the path of 3I/Atlas would have carried it to within roughly 54 million kilometers, a distance potentially close enough for detection and perhaps even coarse imaging. This hypothetical scenario invites consideration of what could have been learned. Assuming a conservative minimum diameter of about 5 kilometers, as suggested by current estimates, the object would likely have reflected enough radio energy for our instruments to register. With multiple radar snapshots taken over the course of its 16-2-hour rotation period, astronomers might have reconstructed its three-dimensional shape, determined its true size, analyzed its spin dynamics, and searched for irregularities that could hint at unusual physical processes or structural asymmetries. The strength of radar reflections depends primarily on two factors: the physical size of the object, which controls the cross-section available to scatter radio waves, and the distance, which has an especially steep influence. Specifically, the detected radio flux scales with the square of the object's diameter, but inversely with the fourth power of its distance from Earth. This fourth power relationship arises because the outgoing signal weakens by an inverse square law as it travels outward, and then the reflected signal suffers another inverse square decline as it returns. The combined effect means that even relatively large objects become effectively invisible to radar beyond a certain point, as the returning echo diminishes too rapidly to be distinguished from background noise. In the case of 3I/Atlas, the difference between a distance of 54 million kilometers and its actual closest approach of 269 million kilometers corresponds to a dramatic reduction in signal strength, dropping by well over an order of magnitude and rendering actual radar observation impossible. Thus, despite possessing adequate size and an interesting rotational profile, 3I/Atlas remained beyond the practical reach of terrestrial radar due to simple geometric misfortune. The Earth was not in the right place at the right time. This leads naturally to the question of what 3I/Atlas actually is, and whether it is unquestionably a natural comet or something more exotic. Based on current evidence, the most probable explanation is that it is indeed a natural comet originating from another planetary system, following a trajectory that brought it through our solar system as an unbound traveler. However, like its predecessors 1I/Oumuamua and 2I/Borisov, 3I/Atlas displays several puzzling characteristics that deviate from the behaviors expected of typical natural comets and asteroids, prompting astronomers to assign it a rank of 4 on the Loeb scale. This scale ranges from 0, indicating an object that is definitively natural with no unexplained features, to 10, representing an object whose properties strongly suggest technological origin. A rank of 4 does not imply artificiality, but signals that the object displays multiple anomalies meriting further investigation. In the case of 3I/Atlas, 8 such anomalies have been identified. These include unusual brightness variations inconsistent with the expected reflectivity of a typical cometary nucleus, a rotational period that is somewhat atypical for an object of its estimated size, and inconsistent ratios between observed light curves and expected sublimation activity. Additionally, its inferred minimum diameter of roughly 5 kilometers, while not extraordinary, is at the upper end of what might be expected for an interstellar comet, which raises questions about how such an object could have been ejected from its parent planetary system with sufficient velocity to escape into interstellar space. Another anomaly lies in its lack of clearly detectable outgassing at distances where water-ice sublimation would ordinarily manifest, although this could be explained by a surface dominated by more refractory materials or by a geometric orientation that conceals jets from our line of sight. Its trajectory also shows slight deviations that are still under examination, and while these variations remain within the bounds of natural explanations, they nevertheless contribute to its lobe-scale ranking. These combined factors do not point toward a definitive non-natural origin, but they do highlight that 3I/Atlas belongs to a growing category of interstellar objects whose characteristics do not perfectly overlap with the objects we regularly observe within our own solar system. Each anomaly, taken separately, may have a mundane explanation, yet their collective presence encourages careful scrutiny and further study. While 3I/Atlas is almost certainly a natural body, its peculiarities remind us that interstellar objects may follow evolutionary paths, unlike anything in our local environment. Their surfaces may be altered by cosmic ray exposure over millions of years. Their internal structures may be fractured by tidal encounters during ejection, and their compositions may include exotic materials formed under conditions not found in our solar system. Because such objects travel vast distances and encounter environments far different from those shaping typical solar system comets, they can exhibit properties that appear anomalous simply because we lack a sufficiently broad comparative sample. The inability to image 3I/Atlas with radar is therefore a lost scientific opportunity. A resolved radar image could have reduced uncertainties related to shape, density, surface texture, and internal cohesion, and might have clarified whether its brightness variations arise from geometry, albedo differences, or something else entirely. Radar could also have helped test hypotheses about whether interstellar comets contain unusual metallic inclusions, complex organic crusts, or configurations produced by unfamiliar formation processes. Although radar observation was not feasible, continued optical, infrared, and spectroscopic monitoring will still provide valuable information, and missions planned for future interstellar intercept opportunities may one day offer direct spacecraft encounters with objects like 3I/Atlas. For now, the object remains an intriguing visitor, one that reinforces the need for improved detection networks, rapid response observation protocols, and perhaps even dedicated interstellar object intercept missions that can close the information gap left by the limitations of Earth-based detection systems. Ultimately, while the evidence at present strongly favors a natural origin, the anomalies associated with 3I/Atlas highlight how much we still have to learn about the diversity of bodies that inhabit the galaxy and occasionally wander into our solar system, offering brief but invaluable opportunities to study the broader cosmic environment from which they emerge.